Hello everyone. In this video, we are going to build a smart contract project using EIP-2535, also known as the Diamond Proxy. Before we proceed into that, let's first understand what Rootstock is. So Rootstock is a smart contract platform secured by Bitcoin that brings Ethereum-compatible smart contracts to the Bitcoin ecosystem. It allows developers to build decentralized applications using Solidity while benefiting the security. The key features of Rootstock are like the Bitcoin level security. Rootstock is secured through merged mining with Bitcoin inheriting the Bitcoin hash power. This makes it one of the most secure smart contract networks available. Rootstock is also EVM compatible, that it's fully compatible with their Ethereum virtual machine, that's EVM. So developers can deploy their Ethereum smart contract without rewriting their code. It's also a smart Bitcoin, that's RBTC. So Rootstock uses RBTC, that's 1:1 like with Bitcoin as a native gas token. BTC can be locked on Bitcoin and used as RBTC on Rootstock for transactions. Rootstock also gives a lower transaction fees compared to Ethereum mainnet. Rootstock offers significantly lower gas fees. This makes it quite suitable for a real world and enterprise grade applications. Also, the transaction that happens on Rootstocks are quite faster. Rootstock has faster block time than Bitcoin, enabling it as a quicker transaction. Confirmations, that's ideal for DeFi payments and tokenized assets. And let us go on understanding all about Diamond Proxy, EP-2535. So EP-2535 defines the Diamond standard, which is an upgradeable proxy pattern for Ethereum smart contracts that overcomes the EVM's KB bytecode size limit by routing calls to multiple implementation contracts called as facets. So the core components are the Diamond serves as the central proxy contract using a callback function to delegate calls via delegate call to specific facets based on function selectors stored in mapping. The facets are modular contracts handling distinct functionalities, while the diamond cut function enables adding, replacing, or removing these mappings for upgrades. So diamond loop function provides an introspection, allowing queries for facets, selectors, and supports. So the key advantage is that this pattern supports unlimited functions through modularity, atomic upgrades for of an individual facet, and a upgrade history log, reducing gas costs compared to single implementation proxies. So unlike any of the transparent or other proxies, it handles multiple logic contracts simultaneously with the function level granularity. So the actual architecture, if we see, of Diamond Proxy EIP-2535 is the diamond component, which has a proxy contract and roots call via selector mapping. Then we have facets, which has the logic implementation, whose features are the modular, independently upgradable. Then we have diamond cut, which is an upgrade manager, which can add, replace, or remove the operations. Then we have diamond loop, which is for introspection interface, which has the query facets and the functions. Then the upgrade process, if we see, is of diamond cut. So this diamond cut function automatically add, replaces, or removes the function selectors via facet cut stubs, each specifying a facet address action like add, replace, or remove, and selector array followed by an optional delegate call initialization on init. So every cut emits a diamond cut event, logging changes for transparency and auditability, preventing partial upgrades that risk data corruption. So replacements reward if selectors match existing facet removals required for prior existence. Then we have introspection features. So Diamond implement iDiamond loop for querying. Facets returns all facet addresses with selectors as facet address selector and it maps selectors to facet address. Facet function selectors and facet addresses aid the UI tool. So this view functions enable off-chain verification of supported functions without gas supporting EIP-165 for the. Then we have gas and optimization. So first is the storage layout. Diamond approach is that it fixed the slot stuffs like Diamond and app storage, and this is shared state across facets. There will be no collisions. Then we have gas stealing, which is the internal function sharing, and it is a fewer X calls. There is optimized facets. Then we can see the scalability in that. Unlimited facets and functions can be seen. There is no size limit, reusable deployed facets. Access to Diamond Cut demands some strict ownership as it enables arbitrary delegate call execution. Function selectors, clashes are prevented by logic checks. Self-destructing facets, risk total deletion. Immutability options include some looking for upgrades, post deployment for trustless operations. Then we have call flow diagram also, and this uh, structure architecture upgrade is for add, where we have the loop selectors for mappings. In replace, it reverts if existing is not equal to the old facet, and in remove, it just clear the mappings and reverts it if absent. So this was all about our EIP-2535 diamonds. So now we'll go on building our Diamond Proxy project. So we've opened RSK Diamond Proxy folder in our code editor. Now we'll just go for doing some project setup. So I've opened my terminal. I will give a command here as npm init y. So this command will initialize a new node.js project in our folder. Then npm install save dev hardhat. So this command will install the hardhat as a development dependency. So hardhat is a development framework that is used to compile, deploy, test, and debug Ethereum smart contracts. So this save dev flag means that hardhat is only required during the development and not in the production. Then next we'll give npx hardhat init. So this command will initialize a hardhat project using hardhat's built-in setup wizard. So here we'll choose the version hardhat 3 beta. Then we'll select here a TypeScript hardhat project using node test runner and VM. Then we'll do it using into ESN. So it has given some files. Now, do you want to run it now? So yes. So this command npx tool runs hardhat directly from node modules without installing it globally. When you run this command, this hardhat has asked us a few questions and then it has automatically created this project structure including the contracts, scripts, tests, node modules. Then we have hardware.config.js file. So in this step, it completely sets up everything that is needed to start writing and deploying the smart contracts for our project. We also need to install some dependencies like OpenZipline contract, the fourth standard library. So we'll give one command for that also. Till this is installing, we'll understand what this Python folders mean. First is contract. So it has some already written contracts here. So we'll delete those. So we are done installing hardhat. We'll give the next command npm install .net.env. So this will install the .env packages, which allows to load the environment variables from a .env. So we are done installing everything for our project. So our setup is ready. Now let's understand all these files first. So contracts. So this folder has all this already smart contracts. So every contract that you want to compile, deploy, or test must live in this folder. Then we have ignition. So ignition is created by Hardhat Ignition. Hardhat's modern deployment system. So it contains the deployment modules. Then we have node modules. So node modules have so many folders that stores all the installed npm dependencies, including the Hardhat, OpenZipline, Ethers, and other libraries. So it is automatically generated and should never be edited manually because it can be very large, as you can see here. It's a large. Then we have scripts. So scripts contain manual deployment and automation scripts. The scripts are typically run using npx hardware run. So before ignition, this is the primary way to deploy the contracts. Then in tests, there are all automated tests we can see for our smart contracts. So tests are written using Mocha, Chai. You have selected your runner and VM. Using these utilities, you can test these files. Then we have git ignore. So git ignore tells git to like which folder should not to be tracked in this version control. Then hardware config ts is the main configuration file for the hardware. It defines the solidity compiler version, network configuration, plugins, path, and environment variable usage. Then we have package log.json. So this file logs the exact versions of every installed dependency. It ensures that anyone installing this project gets the same dependency tree, avoiding works on machine issues. So this file should always be committed to the Git. Then we have package.json. This defines the project's metadata and dependencies. So it lists all the installed npm packages, scripts, and basic project information. Then we have readme.md. So readme.md is a documentation file for the project. So it visually explains what the project does, how to install the dependencies, how to compile and deploy the contracts, how to run the test. So everything is present in readme. So good readme is essential for the open source projects. Then we have here's config.json, which configures the TypeScript compiler options for the project. It defines things like module resolution, strictness, target version, and path analysis. Now let's go on writing our contracts. So in contracts, we'll create a folder and we'll name it as interfaces. Inside interfaces, we'll create one new file and let's name it as ERC165.sol. Now let's go on writing. So this interface defines the ERC165 for interface detection. So it will allow the contracts to declare and expose with the interfaces they support. Now let's give our license identifier first, ETX identifier. Now our solidity version, the Sigma solidity, and let's give our solidity version on 0.0. Now we'll declare an interface. So interface, and let's name that interface as IRC165. So this will be an interface for IRC165 standard, as this allows contracts to declare with the interfaces they support. Now let's give a function as supports interfaces, supports interface, that's bytes for interface ID, interface ID. So this will return true. I will give boolean and bool inside it. So this will return true if the contract implements the interface defined by interface ID. And this interface ID is the XOR of all the selectors in the interface. So this complete IRC165 is a standard interface detection mechanism used across the Ethereum-based contracts. So it will allow a contract to declare which interface it supports using the interface IDs. So other contracts and tools can query this information via their supports interface. Now in Diamonds, it helps expose supported standards like iDiamond Correct, iDiamond Loop. Now let's, in this interfaces itself, we'll create one more file and we'll name it as iDiamond cut. So in this interface defines the upgrade mechanism for diamond contracts as specified in 2535. So this will enable the adding, replacing and removing functions through the facet based upgrades. So starting with a license identifier as usual, then Sigma validity version. Now we'll give an interface as iDiamond cut. So this interface that will define how facets are added, replaced or removed. So this will follow the EIP-2535 diamond standard. Then we'll give enum facet cut action, and in this we'll give add, replace and remove. Add, replace and remove. So this will be an enum to define the type of operation on a facet. That would be our add, like to add new functions from a facet. Replace, that is to replace existing function with the new ones. And remove, that is to remove the existing function. And let's give a struct. So struct facet cut, facet cut, and the inside this we'll give the address to the facet, so facet address. Address. This will give the address of the facet contract. Then facet cut action. Facet cut action. This the action that has to be performed. Add, replace or remove. Then by 4 function selectors. That is, it's an array of function selectors as bytes 4. And each selector represents a function that is to be added, replaced or removed. Then we'll give an event as diamond cut. In this we'll give the facet cut. So there will be list of facet cut facet changes. So underscore the diamond cut. Then we'll have the address. So address in it will have the address of the contract to run the initialization. Then byte call data, that will encode the function call for initialization. Then we'll give a function as diamond cut. That's the main function used to modify the diamond. This will have facet cut, date facet cut, call data underscore the diamond cut. That will have all the facet changes to apply. Then again the address initialization, that's the initialization contract address. Then bytes call data underscore call data, that will initialization of the function call data. External. So this external can be called from outside the contract. So this function updates the diamond functionality at runtime. So this complete iDiamond cut defines that the upgrade mechanism of a diamond contract as per the EIP 2535. So it has allowed the adding, replacing or removing function by specifying the facet address, while facet address as well as the function selectors. The facet cut structure describes each operation, while facet action defines the type of changes, whereas the diamond cut event records all the upgrades on chain for transparency. This interface is essential for making the diamonds modular and upgradable. Now we'll create another file inside interfaces. So let's name this file as iDiamondView.store. So this interface provides read-only inspection functions for the diamond contracts. It allows users to explore facets and their associated function selectors. Let's give stdx license identifier, then the pragma solidity version. We can specify any solidity compiler version about this, that 0.8 point whatever you want. Then interface. So this interface defines read-only function. Now we'll give struct facet. So this will struct representing a single facet and all its functions. So address, that's a facet address, and so the facet contract. Then bytes code the function selectors. What are the list of function selectors implemented by the facet? Then function, facet, external view returns, and we'll give the facet memory facet. So this will return all the facets and their associated function selectors. We'll be giving another function as, like we'll name it as facet function selectors and the address, and we'll give it externally, so external view returns, and inside this we'll give bytes for memory function selectors. So this will return all the function selectors that are supported by the specific facet address. The other function that we'll be giving is facet addresses, external returns. So this will give address, memory, and the facet address. So this will return a list of all facet addresses that are used by Diamond. The last function that we'll be giving is function facet address. In this we'll give bytes 4 and the function selector, and this also will give external and the address of the facet. So address, facet address, this will return the facet address that implements a specified function selector. So this complete contract provides read-only inspection function for a Diamond contract. This improves the transparency and makes debugging and tooling integration quite easier. It is commonly used by block explorers and front-end application. It's one of the mandatory interface in a Diamond standard. Now, in this contracts, let's create a folder and let's just go on naming it as libraries. Inside libraries, we'll be creating a file as libdiamond. This is the library that is the backbone of the Diamond architecture that manages shared storage and upgrade. It handles ownership, facet mapping, and function selector management. Let's begin the code. License identifier, and now we'll give the solidity 0. That's our compiler version. Now we'll be importing. So first we'll be importing import iDiamond cut, and we'll be importing it from our interfaces as we just wrote it. We have it and interfaces slash iDiamond cut dot. So this will simply import the iDiamond cut interface for facet cut stuff and the num. Then let's give a library now. Library, and let's name it as libdiamond. This will be a core library that will manage all the diamond storage and upgrade the logic. And this will give bytes 32 constant. I will name it as diamond underscore the storage position. So this will be a fixed storage slot for diamond storage. Take at 256 diamond dot standard diamond dot storage. So now we'll give the struct facet address. We'll name it as facet address and position, and we'll give the address here, address of facet. So that will be a facet implementing the function. Then uint 96 function selector position, this will be an index in the function selectors array. So this stuff will store the facet address and the selector position. Now we'll go on creating another struct and we'll be naming it as facet function selectors. This will be of type 4 and we'll give here the function selectors, then the function selectors for this facets, and uint 256 facet address position. This will have the index in the facet address array. This stuff will be storing the selectors for a facet and its position in the facet address. Then another struct that we'll be creating here, and let's name it as diamond storage. Now we'll be doing mapping. So we'll be mapping the bytes 4. So from bytes 4, the facet address and position, and here we'll give the selector to facet and position, and position. So this will map the function selector, facet address, and selector position. Now we'll go on mapping again. So mapping this will be from address to the facet function selector. Facet function selector. And here also we'll give the facet function selector. This will simply map facet address to its function selector. Now we'll list all of the facet addresses. So address and the facet address. Facet addresses. Then again we'll do mapping from bytes 4 to bool and the supported interfaces. So this will be in ERC 165 supported interfaces. Then we'll have the address of the contract owner. So this will be an owner of the Diamond contract. Now we'll come out of the struct and create a function named as Diamond storage, and we'll give this internally. So view internal pure returns, and inside this yes. So this will return a reference to the Diamond storage using the assembly. Now here we'll give bytes 32 position is equal to position that's equal to the diamond storage position. Then we'll get the assembly this dot that's equal to the position. Now we'll be creating an event and let's name that event as ownership transfer. So this will be an event that we are creating that would be emitted when the ownership changes previous owner and the address indexed the new owner. So as the ownership changes, emit this event, like we'll be having both previous owner's address as well as the new owner's address. Now we'll set another function as that contract owner, and the address of the new owner. So this will set a new contract owner. Internal diamond storage ds that's equal to diamond storage. Then the address of the previous owner that is equal to ds dot contract owner, and ds dot contract owner now will be equal to the new owner. This will emit ownership transfer from previous owner to the new owner. So this function has simply transferred the ownership from the previous owner to the new owner. Now function contract owner internal view written and the address of the contract owner. So this will return the current contract owner which is set. Contract owner this is equal to the diamond storage dot the contract owner. Now we'll go on reverting function named as enforce is contract owner internal, and here in this will give the require message.sender that will check if it is equal to the diamond storage and the contract owner is, then it will say that the lib diamond, it will give the statement, it will display the statement as lib diamond. This must be contract owner. So this reverts if the caller is not the contract owner. So if the statement is like showing that it's not a contract owner, it happens, then it will display this statement as the diamond must be a contract owner. Now we'll give another event as diamond cut, diamond cut dot facet cut, give the diamond cut, the initialization address and the bytes of call data. Now we'll go on creating another function and we'll name it as diamond cut, diamond cut dot facet cut memory of diamond cut address net the bytes memory for the call data internal, and we'll give a loop now for loop. So for I we'll give the initialization of I has to be, we'll get the condition as I has to be less than the diamond cut dot length, and we'll go on incrementing it. So I diamond cut the facet cut memory cut that has to be equal to the diamond cut I. So this will be a loop through all the facet cuts now. We'll give now if else. So we'll add now new function. If cut dot action, check it, it is equal to I diamond cut dot the facet cut action dot add, and the add functions that would be cut dot facet address comma dot cut dot function selectors. Function select now. We'll go on replacing the existing function. So we'll give else if cut dot action this is equal to, like it will check if it is equal to the I diamond cut dot faucet cut action dot replace. This will be inside the condition. So here we'll write this condition, and the statement inside this will be replace functions, and then we'll give cut dot facet address, cut dot function selector, function selectors. Now we'll give again another, and the condition inside this will be cut dot action, and I'll check whether it's equal to I diamond cut dot facet cut action that the remove. So this is for removing the function. So similarly for this, we'll write remove functions cut dot facet address comma the cut dot facet, else this will be a revert statement. So this is for the invalid action that will happen. So and it will display lib diamond incorrect faucet cut action. That's the end of our for loop. We'll give emit. We'll just emit the diamond cut event now. So emit diamond cut, and we'll give diamond cut the init and the call data. So we'll limit all of this, and then we'll do some initialization logic. So initialize diamond cut init mother call data. So we'll just initialize this, and now we'll go on doing another function in which we'll be adding the functions. So we'll name this as add functions. So we can we can just add new functions to the facet. Then by for the memory function selector, memory function selector, and we'll give this internally. So internal, then we'll give the required statement. The condition will be the function selectors, the length of the functions that is being selected has to be greater than 0. If not, then it will display lib diamond cut no select. So this is the message that they will be displaying. Then diamond storage DS, that is equal to the diamond storage. Then another require will be giving with the condition that facet address is not equal to 0, like any address 0, that is any invalid address. If so, it happens, it will display a message that is lib diamond facet is 0. This is the message that they will be displaying if this condition is true. Like if this condition is false, the facet address is equal to the address 0, then this will be the condition that will be displayed. Now we'll give the, like we'll get the current selector count. So for this, uint36 selector position, that's equal to uint96 ds dot facet function selectors and the facet address inside it dot the function selectors dot length. So this will get the current selector count. Now we'll go on adding some facet address if there are any new. So we'll give if and let the condition be selector position is equal to 0. So we'll check if the selector position is 0 or not, and if so, it will go on adding the facet address. So ds comma the facet address. Now we'll add each selector. So for that, we'll give a loop, for loop, and we'll go on initializing I first. So uint 256I. Then the condition would be I has to be less than the length of the function selectors. So function selectors dot length, and then we'll go on incrementing it inside this. All right, bytes for selector that is equal to the function selectors inside it. And then we'll give a require statement, and this will give ds dot selector to facet and position, and we'll give the selector here the facet address. It will check if the address is valid or not. So address 0, the function exists. If the facet address is valid, then the function would exist anyhow. Then we'll be giving add function, the ds selector position, and the facet address. And then we'll go on incrementing the selector position. Now let's replace all of the existing functions. So for that, function replace functions, and now we'll give the address of the facet, then the memory for our function selectors, memory selectors, and now we'll go on giving it internally. So internal, and now we'll give the require, and the condition would be the length of the function selectors to be greater than 0. So this is true. So this will be replacing all this function is for replacing all the existing functions. First, we'll check if there is an existence of the selectors or not. It will display libdiamond, no selectors. If the function selector length is less than 0, no selectors. Now, diamond storage, yes, that's equal to the diamond storage. Then we'll give another require, and this will give the condition as facet address that's not equal to address of 0. It will display lib diamond cut facet is 0. You also should mention lib diamond cut, then uint 96 select the position that is to be equal to uint 96 the ds dot, and then we'll give the facet address to it dot the function select dot the length. Then we'll give our, and inside this we'll give the condition as selector position. We'll check if it is equal to 0. If yes, then we'll just add the facet address here. Now we'll go on creating a for loop. So for there will be initializing I will give the condition as I has to be less than the function selector length, and I will do the increment of it as last plus. Inside this, now we'll give our statements. So bytes for selector is equal to the function selector I, selectors, then address of the old facet, address of the old that is to be equal to the selector to facet and position, the selector dot the facet address. Now in the require, we'll give the condition as old facet not equal to the facet address. If this condition is false, it will give lib diamond cut. Then we'll use a remove function. Yes, old facet and the selector. Then add function, then ds, the selector position, and the facet address. And I will go on incrementing the selector position. Now we'll give another function for removal of the existing functions from the diamond. So for that, we'll be giving a function as remove function, and the starting things all are going to be same. So we'll just copy it, paste it, and do the required changes. So here, let's name this function as remove function. And our address will be facet address. the bytes memory function selectors, and then internally we'll give a require, and inside that the condition would be the same, function selectors dot length greater than 0, this storage, and then the facet address must be zeros for removals. So for that we'll check that facet address is equal to address 0. If then we'll display lib diamond cut 0. Then we'll go on giving a for loop now. Yeah, similar for loop. For I will complete this down. So for u in 256 we have given I will have the semicolon. So we have initialized I. We have given a condition that it must be less than the function selector's length, and then we've incremented it, and by for selector that would be equal to the function selectors. Then address of old faucet that's equal to the selector to faucet position and the facet address. Then here we don't require to have it. There's a necessity of giving this require. Then we'll give this remove function with old facet selector. Now we'll go on giving another function for adding the facet. So function add facet, and then the diamond storage, the address, so facet address, and we'll get all of this internally, so internal, and then we'll write in this ds dot the facet function selectors, facet function selectors, that's dot facet address position. This all would be equal to facet address position. This would be equal to dot facet addresses at the length ds dot facet addresses. So this was to add a new facet address. Now we'll go on adding a function. So function add function, and then we'll give the diamond storage ds the selector. So bytes for selector, the unit uint 956 selector position, then the address of the facet, so address, facet, address, and then again internal. Then we'll give ds dot selector to facet and position selector. So this will simply add a function selector to our facet address and position, and we'll give the facet address first, and then the selector position dot facet function selectors, and the facet address dot the function selectors dot push selector. Now another function for removal, function remove function. So we'll give again the same diamond storage ds the address, asset address, then the selector bytes for selector, then we'll give. So this will remove the function selector. Now in require we'll facet address. So the condition for facet address should not be equal to address 0. It must be a valid address. If the statement is true, then lib diamond cut would be function message. So this will be the message that will be displayed. Then another require. In this, the condition that we'll be giving is facet address is equal to is not equal to the address of this. So the message that we want to display would be diamond cut immutable. Then UN256 selector position that's equal to ds dot selector to facet and position selector dot function selector position. Similarly, we'll give for last selector position as well. So we'll define or declare another UN256 and name it as last selector position, and this would be equal to ds dot facet function selectors. In this will have a facet address dot the function selectors at length -1. Now we'll go on swapping the selectors. So for that, we'll give if, and we'll give the condition in this if the selector position not equal to the last selector position. If this condition is true, then this will be executed. Bytes 4 will first give last selector. We'll give declare last selector that would be equal to ds dot facet function selector facet address dot the function selector dot function selectors and the last selector position inside this. Similarly, we'll be giving this again, but now we will be giving this for the selector position instead of last selector position, and this complete would be equal to last selector. Then ds dot selector to facet and position, and we'll have the last selector in this last selector function selector position. This would be equal to uint 96 selector position. So this was swapping of selectors with last. Now we'll go on removing the selector. So for that we'll have ds dot facet function selectors, the facet address dot function selectors dot pop, then delete ds dot selector to facet and position, and then I'll have the selector here. So this will help us remove the selector. Now we'll go for creating another function as initialize diamond cut, and this in this will give address in it, then the call data, so bytes memory call data internal. So this is to execute the optional initialization logic after the upgrade. So for this we'll give now if and let our condition be init. We'll check if it's equal to address 0, and then we'll give an require, and the condition would be that length of the call data dot length, if it is equal to 0, we'll check the call data length. If this condition becomes true, if the length becomes 0, and if does not come 0, then it will display a message as call data, not empty. Hence, we'll give require if call data length is greater than 0, then libcut will, and that displayed message is to be lib diamond cut call data empty. If this condition is false, then it will display this message. We'll give if inside else, we'll be giving if. So if the condition is init is not equal to the address of this, if it's not equal to address of this, enforce contract code. Enforce contract code init, and the message that would be displayed would be lib diamond cut no code. Lib diamond cut no code. Now we'll give the bool success the bytes memory error. This would be equal to init dot the delegate call, and we'll get the call data here. And then again if, and if the condition would be if it's not successful, not success, then again we'll give it inside if, that is the error of length. So the error length is greater than 0. If this condition is there, and we revert it, we'll be reverting it. So revert string error, string revert, and the message will be displayed as lib cut diamond cut init field. Now the last function that we would be creating is enforce has contract code, and enforce has contract. Also we have taken enforce has contract. So in this we'll be adding address of the contract, then the string memory and the error message. Then we'll give this internally, so internal view, and we'll first declare a contract size for this contract size. In the assembly, the contract size is not like is, we'll give this, and that's in code size. And then last we'll be giving required statement require, and then this the condition would be the contract size has to be greater than 0, and then the error messages will be given. Error message. So that's it. That's all about our libdiamond library. So this complete library is the core of the Diamond structure that has completely managed all the shared storage for all facets. It has also handled all the ownership, facet mappings, function selector management, and has implemented the internal logic for addition, replacement, the removing functions. It is also supporting our run65 interface detection and upgrade initialization. So all the facets which are there that rely on this library to interact with the Diamond storage safely. That's it for this part. We have finished setting up all the interfaces and libraries that act as the backbone of our system. So in the next part, we'll start writing the actual facet contracts and then bring everything together inside the main contract. So see you in the next one. Thank you.